Welcome back. So trigonometric ratios for kind of three special cases of angles. Now these angles, so 30 degrees, 45 degrees, and 60 degrees, they do come up quite often enough in math and sciences just because of symmetry that happens within different structures, different things we do, that it's kind of useful to be able to know the trigonometric ratios, all for cos, for sine, for tangent, for these particular angles. And you might think, oh my gosh, that's going to be a lot to remember. I'm going to try to break it down. I'll show you where it kind of comes from. It does come from pure symmetry of a square and then pure symmetry of an equilateral triangle, where these angles actually dominate quite a bit. All right, so let's take a dive in. If you have a square, and it doesn't matter what the sides of the square are. So I can arbitrarily call this, let's call that each side of the square is of length A. And if you take this particular square, and let's say you wanted to be able to divide it up. So let's say I do something like this, where I basically split it into two equal triangles. Now, these triangles, because it's a square, they will have or they will construct an isosceles right-angle triangle. So here is your right angle because it's a square, and then all the sides are the same. So it's basically an isosceles triangle, and it's a right-angled isosceles triangle. So what that tells us is that these angles right here must be 45 degrees. And again, that should make sense to you, because if you're going to be dividing the square in half, well, then you have 45 degrees and 45 degrees on each side. And now, if you wanted to be able to find what the trigonometric ratios are related to this 45 degrees, it doesn't matter if it's sine, cosine, tangent, and so on, I want to try to show you how you can derive it just basically out of this. And then I'll show you kind of how to remember it, because you don't have to take an arbitrarily side of length A, meaning any A. You can actually, we can do this and set A is equal to 1, because trigonometric ratios work for all similar triangles with exactly the same angles. Okay, so the only thing that I really don't know is my hypotenuse here, right? But my hypotenuse is kind of very easy to be able to find, because that hypotenuse that I have, let's call it h, is basically, or h squared, is equal to a squared plus a squared. And this, if I take the square root of this, so you will notice that what's going to happen, okay, so this is going to be 2a squared, well, because a squared plus a squared, we have two of them. And now all of a sudden my h becomes the square root of 2, and it's being multiplied by this a. Okay, so multiplied by a, I'm just going to write the a in front, okay, of the radical. So this is my hypotenuse. And notice, so, it doesn't matter what the length of that particular a is. And now if I go and try to find my trigonometric ratios for this 45, so what we have, if I take, for instance, cos of 45 degrees, you know that this is just simply adjacent over hypotenuse. But what does this equal in this particular case when it's 45? Well, my adjacent, and it doesn't matter which side you pick because they're both 45 degrees. So this is going to be just a, which is the length of my side, divided by the hypotenuse, which again is just a, okay, and times the square root of 2, because that's the hypotenuse. So the a actually cancels. And what this is it's going to just give you 1 divided by the square root of 2. And the key thing here is that notice that the length of the sides is irrelevant. And that's what really trigonometric ratios are, right? We don't really care what the sides are. We just are interested in the ratios themselves. And now you can do the same thing. So I can take this and write it out for sine. So sine of 45. This is opposite over hypotenuse. And again, you're going to get a divided by, in this case, over hypotenuse, which is a over the square root of 2. Again, your a's cancel. And it turns out that this is just 1 over square root of 2. So the cos and the sine ratios are identical whenever it is 45 degrees. And that really shouldn't surprise you because those lengths are identical, right? It's an isosceles triangle, okay, of equal lengths A and A that we have in there. So that's why the ratios would be the same. Now, if you would try to take the tangent, so the tangent of 45 degrees, then what you have, you know that this is opposite, okay, over adjacent, so opposite over adjacent in this case, or really it's also just sine over cos, right? That's how tangent can also be defined. And if you do this, well, opposite over adjacent, this is just simply A divided by A, right? Because those are the actual lengths of the side. And by definition, then this, okay, these cancel. This is just equal to 1. And those are the actual trigonometric ratios for 45 degrees. So it's not very difficult to be able to find them. And you notice that in all the instances, the actual length of that original square, so length A, is irrelevant. It doesn't matter what it is because it's going to cancel each other off. So what most teachers or even professors or instructors or students, anyone learning this, most of the time what people will do is, instead of trying to, derive this and set it up in terms of some random side of length A, because the A always cancels, you will find that this most of the time will be derived, and someone might show it to you with just sides equal to 1. And then the hypotenuse, therefore, is just going to be the square root of 2, which should make sense, right? Because if the sides are 1, so notice right here, okay, on the top right, what I'm just kind of checking off there, if the A is equal to 1, then indeed hypotenuse is going to be the square root of 2. And this is how people most of the time will remember this 45 degrees. So even if they forget, like for myself, I sometimes forget if I don't use it. So what I do is I just draw this square, okay, just cut it in half, set the sides equal to 1, and then it's very easy for me to be able to derive, adjacent over hypotenuse, opposite over hypotenuse, opposite over adjacent, and so on. Now, from these ratios, you can also find the secant, right? The cosecant, and then also the cotangent of all of these, because those are just simply the reciprocals. So for instance, if you wanted to find the secant, then all you would do, well, secant is just 1 over cos, okay? And that means the reciprocal is just square root of 2 over 1, and there you have it. So this is your secant. If you want to find your cosecant, well, it's just 1 over sine. So that means we're going to take the reciprocal, okay, of our sine, which again is going to be exactly the same thing. And now for the cotangent, well, the reciprocal is 1 over tan, but tangent of 45 is 1. So therefore the cotangent is also going to be 1. So you can have those as well. And those would be all of your actual trigonometric ratios for this 45. And then you notice that they're actually not that difficult to try to remember. And I encourage you, think of this. So instead of just setting a general A, which you can do, I showed you this, I've derived it in terms of a length A of a square, you can just set the length to be equal to 1. And that's what you will find. And later when you study, for example, the unit circle, kind of, the nemesis of students for trigonometry, the reason for setting it to 1 is because really it doesn't matter what that length could be. We will have exactly the same ratios for our trig ratios that we set. Now, I said that, we are interested, so this is really just 45. So now, well, what happens to 30 and 60? Okay, in those cases, and where does that really come from? From what kind of symmetry? Well, this is a square, so we got the 45 degrees from a square, cutting it in half. And now the other aspect is, okay, an equilateral triangle. Okay, so now coming to this equilateral triangle, and I guess, what I'm going to do is I'll set because it's an equilateral triangle, so let's set all the sides to A. You'll see that it won't really matter that it's A of kind of arbitrarily size when we do our trigonometric ratios, but I'll set it to A anyways. Now, because all the sides are the same and it's an equilateral triangle, that means all the angles are the same, so my interior angles are 30 degrees. Now, what I will do is, just like with the cube, is I'm going to draw up a line here, which is going to be kind of a perpendicular line to the base. So this is going to be 90 degrees. And I'm going to be working with the actual triangle itself. So not the equilateral triangle with the 60s, but instead, with this triangle which is cut in half of this equilateral triangle to get our ratios for 30 and 60. And of course, because we cut it in half, that means this angle right here is 30 degrees, and of course the other one is going to be 90 degrees. Now we have to be careful a little bit. We are missing, okay, the dropped line. Now that's not your hypotenuse because the right angle, okay, notice is at the bottom. So our hypotenuse in this case is actually our A right here. Now this side, or at least from here to here, so this is going to be A over 2 because we cut it in half. And then this side right here, well, we don't really know what that side is, but we can find it again by using Pythagorean theorem. So by Pythagorean theorem, we know, okay, so the hypotenuse, which in this case is A squared, because that's opposite the 90 degrees, is equal to, and that's going to be A squared over 2, okay, and this is actually, the whole thing is squared, so I got to kind of be careful how I write it, okay, plus, whatever this unknown is, okay, right here, which is going to be squared. So if I bring this over to the other side, then what I will get is I'm going to get A squared minus, this is going to be A squared, I guess I'll put this over 4, all right, because if I square that 2 at the bottom, and that is equal to, this right here, this unknown. So taking the square root of both sides, so what I have is I have the following. So I have A squared minus A squared over 4, okay, is equal to whatever that is. Now this doesn't really look very pretty, but I mean, I can take out the A here. I can factor out the A. So I'm going to factor out the A. It's going to be 1 minus, and this is going to be just 1 over 4. This is all under the square root. All right, so this is what we have. And now this, okay, so this right here, 1 minus 1 over 4 is really 3 over 4. Okay, so that's what this is equal to. So now if it's going to be, so I'm going to write 3a squared over 4. Okay, and I have to take the square root of that. But notice that taking the square root, what this is going to be is, taking square root of 3, I mean, I just have the square root of 3. But taking square root of a squared, that's going to be just an a. And then taking the square root of the 4 in the bottom, that's going to be just 2. So notice what I have is basically this right here. That's what I will get. And so that unknown side, I mean, instead of writing it the way that I've written it, okay, I can nicely put it like this. A, and then this is going to be 3 over 2. Okay? So that is this side right here. So it doesn't look very pretty at the moment, but you will see that it gives us nice ratios that we're going to get through all the different sides. All right? Okay, so now let's pick one. Let's say we want to be able to know the trigonometric ratios, for instance, for the 60. So what will those be? Okay, well, so cos, okay, of 60 is again, so this is just adjacent over hypotenuse. So this will be equal to, so a over 2 divided by, okay, and the hypotenuse is a, all right? So notice what happens to the a, so the a's will cancel. And so on top, all you're going to have left is just 1 over 2, okay? So that is cos of 60, basically a half. Well, that's nice, and then the a's canceled out. Okay, what about cos, okay, cos, sine of 60? So So if I take the sine of 60, so that is opposite over hypotenuse. Well, the opposite is a, and 3 over 2, but the hypotenuse is just a. So again, the a's cancel, and my answer is going to be 3. So square root of 3 over 2, and that is your trigonometric ratio for sine of 60 degrees. So here is one, here is the other. And then finally, tangent. So if you take tangent of 60, this is opposite over adjacent. All right, so that's what this is equal to. Well, opposite over adjacent, okay, so what does that give us? So the opposite is a, so 3 over 2 divided by a over 2. So look what happens here. Well, the a's cancel. All right. And then in the denominators, so the 2's will cancel. That's what you will see there. So that's just understanding of fractions. So basically what you have is this, because you're dividing. So if you're going to be dividing, so that 2, okay, is going to go up on top. So it's kind of like this. So that cancels there. And what does this give us? Square root of 3. So that's the tangent of 60 degrees. And so there you have it. So those are actual ratios that you have for 60 degrees. All right. And now again, you can take the secant, you can take the cosecant, you can take the cotangent by just taking the reciprocals of these. Okay, so for example, secant would have been equal to 2, because if you take 1 over 2 and you take the reciprocal, it's going to give you 2, and so on for the others. So those are the actual ratios. And what I wanted to point out to you, notice that in this case, again, the a, so the length of the equilateral triangle is irrelevant. It just cancels off in all the ratios. And in fact, for what most people will do is instead of using a, okay, they will just substitute numbers in there. Now here you have to be a little bit careful, but what you can do is, you can take out the a entirely and substitute it with, a number that you like, a 1, a 2, okay, whatever's convenient. All right. So, and I'll do that kind of at the end just to show you. A convenient thing for a in this case, unlike the first one, is you can set a equal to 2. And the reason for that is because it will get rid of your division by 2, okay, that you have in the denominator. Okay. So now, what about 30 degrees? Okay. So what if you do that? So if I set 30 degrees, and I wanted to find out, so if I say cos of 30 degrees, what is this equal to? So again, so it's adjacent over hypotenuse equals 2. And if I go in here, so now adjacent is actually, so in this case, it is equal to a square root of 3 over 2 divided by, okay, and my hypotenuse is a, so this cancels, and it gives me square root of 3 over 2. Okay, so that's what I have in here. And you can now take, again, sine of 30 degrees equals to opposite over hypotenuse. Okay, so now opposite is actually a over 2. So this is going to be a over 2. Hypotenuse is a, so the a's cancel. I'm going to get 1 over 2 remaining right there. And then my tangent, so my tangent of 30 is equal to opposite over adjacent. All right. So in this case, opposite is a over 2. So that's going to be a over 2 divided by, and my adjacent side is a square root of 3 over 2. So again, so the a's cancel. Now the 2's will cancel, and here you're going to just get 1 over that. All right. And you should notice a pattern here between the 60 degrees and then the 30 degrees that you have, that they kind of swap. The cos and the sine swap, and then the tangent is basically just the reciprocal. Okay, so that is exactly what you have. And to remember this, so if you take this and if you forget for whatever reason, and it may happen to you, I mean it happens to me, so copy. So I'm gonna just so that you don't have to rederive and then set this A. Okay, so what I will do is, because you see that the A cancels everywhere, so what I suggest, set A, in this case, just simply equal to 2. Okay, so if you set A is equal to 2, so notice what will happen. I'm going to remove the A and just set it to 2 because it doesn't really matter. It will cancel in the ratios themselves. So what you will get is, you will get this. Okay, I'm going to try to redraw this triangle. Okay, and this is now 2. Notice the 2 and the 2, so that means this is square root of 3. The 2 divided by 2, and this is 1. And this is your 60 degrees, and then this is your 30 degrees. So if you forget, let's say, what's cos of 30, you can take this and then rederive it. Okay, and then just say, oh, cos of 30, that is, adjacent over hypotenuse. So that's going to be square root of 3 over 2. Okay, and that's exactly what you see right here. Now, some questions, so here's some examples that I, provided for you, is because you're going to be asked, and you may not be, utilizing your calculators right off the bat. And even if you do, because you forget, which is fine, sometimes when you have these 45, 30, and 60 degrees in the back of your mind, then you can kind of very quickly find out what answers might be. So for example, if you are given this right here, 1 minus the tangent of 45 degrees. So 45 degrees, the tangent, right, which was the opposite over adjacent, and the sides were actually equal to 1. So you know that this, oh, hey, wait a minute, this is 1 minus 1, so this just equals to 0. And you can very quickly, just substitute and then find what the answers are. Or for instance, if you take this, let me kind of copy it, paste it here. And if you wanted to be able to find this without using a calculator, you can say, oh, okay, this is 2. Now, what is the cos of 30 degrees? Okay, so cos of 30 degrees, so this is what we did right here, which is square root of 3 over 2. Okay, so this is square root of 3 over 2 plus 4, and now it's multiplying sine of 60 degrees. Okay, and if you may remember, 30 and 60, they're kind of swapped. So this is also going to be square root of 3 over 2. All right, so you might see this. So notice, I'm going to just go back to show you. Okay, so you have, okay, so right here, here's your sine, okay, of 60, which is square root of 3 over 2, in case you were doubting. And now you can go ahead and simplify, right? So notice 2 and 2 cancel, so this is square root of 3. 2 goes into 4 2 times, so this is just that. Oh, so this is just 3 square root of 3, right? And that's kind of how you can use, these things. Now here's another one, so here is show that. So here it says show that this, now you may remember this from grade 10. I want to just post this up in here. And by the way, so within here, just if you've forgotten, so when you write sine or cosine or tangent and you write squared and then you put the angle in, this actually means that you are squaring. So this means sine theta times sine theta. That's how we write it. We don't write the square, because we typically, when we do exponents, we would write them at the end. But if you write it at the end, then sometimes there is confusion. And then people think, do you mean, are you squaring the angle? So we typically will write the square, okay, right after. So sine squared or cosine squared, and then we write the angle. And that's what it means. So here, so what we have And this is a trig identity. Okay, so this for any angles, when you put sine squared and cosine squared of an angle, this actually equals something. And it's going to be equal to 1, but let's just show it. So tangent of 45 we know is equal to 1. Now, sine of 30 degrees, okay? So for that, so sine of 30 degrees is just equal to 1 over 2. Okay, so that is that, and now we have it squared. Now, cosine of 30, so if you may remember, so cosine of 30 is going to be square root of 3 over 2 squared. Now, if I square this, it's going to be 1 over 4 plus, this is going to be 3 over 4, and what does that equal? To 1. So, indeed, this is exactly what it equals. So 1 is equal to 1. Here is the final example that I have for you. So what you have in this example is they want us to find the area of the, I guess, the big triangle here. They do give us the tangent of that theta, which is equal to 1. So, well, let's break it down and see. What do we need, right, to find the area? Well, we need, if we have the base multiplied by the height, okay, of the triangle, and we take the half of that, then we will know what that area is. So we know that this is the base times height, okay? Now, we know the height is 10, but we do not know what the base is, okay? So the base is basically the distance between A and C. Okay, let's try to find out. So tangent of theta, so this is equal to 1. Well, we know, okay, so that particular ratio, so we know that that angle must be 45 degrees, all right? And so if that's the case, if it's equal to 1, that means it's 45 degrees. So this is opposite over adjacent, which is equal to 1, which means, now, notice that the opposite is equal to 10. They give you that right here. Okay, so that means the adjacent has to be equal to 10. So I know that this distance, at least from here to here, must be equal to 10. Okay, so that's 1. Now I need to know what the distance now here is between here and here. And if I add those up, then I do know what that base is. Let me try to use, okay, so I have this 60 degrees, all right? Now, so that would be, I guess I can, so what I can use is, so this is going to be the opposite over the adjacent, okay, because it's now, and that's going to be 10 tangent of 60, right? Now, so what is the tangent of 60? So once we have that, okay, so let's kind of go back in here. So remember that tangent of 60, okay, so where was it? It was right here. So that's just equal to this. So the square root of 3. And so for that, so this is equal to square root of 3, which is opposite over adjacent. Now my adjacent is equal to 10. So that means that my opposite is equal to 10 times square root of 3. And that's this distance, 10 square root of 3. So, well, now I can find my area. So my area is 1/2 base. The base is 10 plus 10 square root of 3 times my height, which is 10. Okay? And that, there you have it. I mean, you can simplify it. 2 actually, goes into 10 5 times. You can say that this is 5 times 10 plus, 10 over square root of 3. That would have been your area in whatever units that they're using, which would be squared. All right. So there you have it. So those are some examples that you have within these. They're kind of useful to be able to utilize. You can, make a little chart for yourself. And actually, you know what? Let me make a chart so that you can even take a snap picture. I'll make a chart in fast forward fashion for you in terms of a summary. Okay, so here is the summary. So you have sine, cos, and tangent. 30, 45, 60. You can do the same thing for, secant, cosecant, cotangent, if you like. Those are just reciprocals of all of these. Now, don't feel bad if you kind of don't remember these right off the bat. I mean, 45 degrees is probably the easiest. The other ones sometimes might give you a headache. You can always think of some, visuals going back to that equilateral triangle, and then the square, and then think of it that way. So thanks for watching. See you in a future video. I hope this was useful. Bye, everybody.